In the previous videos, we learned different concepts regarding ADC. We learned how the ADC works. We learned how a signal is sampled and quantized. Now in this video, we are going to see different types of ADCs. There are many ways developed to convert an analog signal to digital, and each way has its own strength and weakness. The choice of the ADC for a given application is usually defined by the requirements you have. That is, if you need speed in conversion, then you use a fast ADC. If you need precision, then you use an accurate ADC. If you are constrained in space, then you use a compact ADC. So basically the different types of ADCs are categorized in this way. So let me list out some of the common ADCs that we use that we use in most of the microcontrollers. So the first and the most common type of ADC that is used is SAR ADC. Now the SAR stands for successive approximation register. So the SAR ADC is the most widely used ADC in the microcontrollers. Then the next is flash ADC, then sigma delta ADC, and dual slope ADC. Now these are some of the common ADCs that are used, and there are some more also. But in most of the microcontrollers, as I said, SAR ADC is widely used. Now why is it widely used? Because due to its low power consumption and high resolution and accuracy. So for this reason, SAR ADC is widely used. Now to understand SAR ADC, let us first understand what is successive approximation algorithm. Now for understanding successive approximation algorithm, let us consider this scenario. Now assume that at this point your input voltage lies. Now from this figure you can figure out that your input voltage is somewhere around 2 volt, but you don't know what it actually is. So let us find out. So how will we find out this input voltage? So we will find out this voltage by comparing it to the reference voltage. Now our reference voltage is this 5 volt. Now let us compare. Is it less than 5 volt? Then yeah, it is certainly less than the reference voltage. So it comes under this whole region. Now let us compare that is it less than half the reference voltage? That means is it less than 2.5 volt? So yeah, it lies in this region only. So as it is less than this 2.5 volt, will give it a value 0. Now let us successively approximate this region again and let us compare that is it greater or is it less than this whole region. So it is greater. So now the area has decreased and now we know that our input voltage lies in somewhere in this region. Now as it is greater than the half voltage of this region, let us give it a value 1. Now let us again successively approximate this area. Now is it less than or greater than? So it is less. So let us give it a value 0. Now again successively approximate this area. Is it less than or greater than? So it is greater than the half this area. So let us give it the value 1. So we have gone 4 steps, 4 levels. That means this is first bit, this is the result for second bit, this is the result for third bit, and this is the result for fourth bit. So basically the combination of voltages that we got for this much region, it is 1010. Now if we convert it, then it is 5. Now let us take another example. let's say this is your input voltage, and you have to find what the actual voltage here is. So as this voltage lies in the this region, and as it is greater than 2.5 volt, we will give it a value 1. Now we will compare that does this lie in the less than the half of this voltage region or greater. So it is greater, so we will again give it a value 1. Similarly here it is lower, so 0, and here also 0. So the value that we get here is 1100, that is 12. Now these are the output bit values that we are getting after converting. Uh, but how do we convert these values into appropriate voltages? Now what is our range and what is the resolution of this ADC? So this is a 4-bit ADC, right? So the 4-bit conversion of 0 volt here would be 0 0 0 0, and the maximum conversion of 4-bit would be, for 5 volt it would be 1 1 1 1, which is 15. So now if we have to find the appropriate input voltages for these two values, then it would be V in equals to what is the reference voltage, that is 5 volt, divided by what is the resolution, so it is 2 raised to n. Now for 2 raised to 1 it would be 2, for 2 raised to 2 it would be 4. So here we are taking the values up to 4 bit, so it is 2 raised to 4, that is 16, into your result. Now what is your result? So 5 and this 12, these are our 4-bit conversions of for this particular input voltage. Now let us put these values over here. 2 raised to n is 16 into 5. So let us calculate. 5 into 5 divided by 16. So it is 1.56. 1.56 volt. So the voltage that we are getting at this point is somewhere around 1.56 volt. And for this case, it would be 5 volt divided by 16 into our result 12. Let us calculate. Which is equal to 3.75. The appropriate value, voltage value for this 4-bit converted value 12 is 3.75 volt, and 4-bit converted value 5, it is 1.56 volt. Now what we observed here is, in successive approximation algorithm, the value that we need to process is being compared with the maximum value. That is, in our case we needed to find the input voltage, that is we needed to find the input value which we found as 1.56 volt. But what we did to find the 1.56 volt, so first of all we compared it with the maximum voltage, that is 5 volt. So was it less than or greater than 5 volt? So it was greater than 5 volt. Then we compared that, was it less than 2.5 volt or greater than 2.5 volt? Then it was less than 2.5 volt. Then we again guessed that was it less than 1.75 volt or was it greater than 1.75 volt. So in this way we successively approximated up to the extent that the range for finding the our output become very small, and ultimately we reached our aim. So in this way the successive approximation algorithm works. Now, as we understood successive approximation algorithm, now let us understand what is successive approximation ADC. So this is the main block, that is successive approximation register, and as you can see on your screen, there are four outputs that are being taken from the successive approximation register. Now the output of the successive approximation register depends on the resolution of the ADC. Now here we are considering a 4-bit ADC, hence 4 output are being taken, and the same output is being provided to the digital to analog converter, which will convert this input binary values to the appropriate output voltage, and that voltage will be provided to the negative terminal of the comparator, and on the positive terminal of the comparator we are providing our input voltage, and that same is being provided to the successive approximation register again. So as this is a 4-bit ADC, so there will be D3, D2, D1 and D0 in the output, where D3 will be the MSB bit and D0 will be the LSB bit. So let us see how this works. So in the initial stage the output would be 0. Now when you provide a input voltage, that is, let us consider 5 volt as input. So when you provide 5 volt as input, what this successive approximation register will do is it will make the MSB bit as 1 and keep the rest of them as they are. So making the MSB bit as 1 generates a 8 volt signal in the output of the digital to analog converter. So now the comparator will compare. Now is the 8 volt less than 5 volt or is it greater than 5 volt? So here the MSB bit successive approximation register makes the MSB bit as 1, and then the comparison happens, that is 8 volt less than 5 volt or greater than 5 volt. So 8 volt is greater than 5 volt, or you can say 5 volt is less than 8 volt. So what the successive approximation register will do is it will lower the range. So it will make this MSB bit as 0 and make the next MSB as 1 and rest of the bits as they are. So making the next MSB as 1 generates a 4 volt signal in the output. So it will make the first MSB bit as 0 and next as 1. So it generates a 4 volt signal. Now again the comparator will compare that now the last signal, the 5 volt was less than 8 volt. Now the comparator, now this successive approximation register has lowered the DAC value and it has come down to 4 volt. So now it is comparing the input voltage with the 4 volt. So now it is checking again, that is 5 volt less than 4 volt or greater than 4 volt. Now the 5 volt is greater than 4 volt. So now what it will do is it will keep the bits as they are and it will increment the next MSB bit again. So now in the output you get 6 volt. Now getting 6 volt in the output again, now it will, now what the comparator will do again is it will compare with the input voltage, that is 6 volt greater than 5 volt or less than 5 volt. So now 6 volt is greater than 5 volt, but it is not 5 volt yet. So what it will do is it will again make the last MSB bit as 0 and make the last bit as 1. So now what is happening here is a 5 volt signal is generated at last, and it will compare the again with the input voltage, and both the DAC value and the input value are same. Then the comparator will trigger the successive approximation register and it will trigger the end of conversion bit, that is EOC, that is end of conversion, and SOC, that is start of conversion. So there are basically two bits. In order to start the ADC conversion, there is a bit known as start of conversion, and in order to end the conversion, there is a end of conversion bit. So start of conversion we have to provide, and the end of conversion is being triggered by the ADC. So if the value of the comparator matches, then this end of conversion bit is triggered and the output is obtained at the 4-bit output of the successive approximation register. So in this way the successive approximation ADC works.